All right, let's get right into it. Every network, whether it's the internet, a power grid, or even just a social circle, it has weak spots. These are points of failure so critical that if they go down, well, the whole system can just fall apart. Today we're going to learn exactly how to find them, using some really cool ideas from graph theory.
Just think about that for a second. An entire city plunged into darkness. Communications are cut, chaos starts to set in, and all because one single cable got severed. Now, this isn't just some movie plot. It's the very real danger of network vulnerability.
That one critical piece has a name. It's a single point of failure. And in this explainer, we're not just going to talk about it. We're going to give you the exact logical toolkit you need to pinpoint these critical weak spots in any network where the connections go both ways.
So our first step is to really nail down what we're looking for. What does a weakest link actually look like when we're talking about graphs?
The easiest way to wrap your head around this is with a simple analogy. Just picture a map of cities, all connected by roads. A weak link could be that one major city that acts as a hub for all the traffic, or it could be the only road that leads into an isolated town. If you take either of those away, somebody gets cut off. That's what we're hunting for.
Now, to be a little more precise, these weak spots actually come in two distinct flavors. In the world of graph theory, we call them articulation points and bridges. Let's break down exactly what each of those means.
Okay, first up, the articulation point. The crucial thing to remember here is this is a node. It's a city on our roadmap, or maybe a server in a computer network. If you pull this one node out, the graph literally splits into two or more completely disconnected pieces. It's that central hub whose failure would isolate entire sections of the network from each other.
And its counterpart is called a bridge. Now, a bridge isn't a node, it's an edge. It's the connection itself, the road, the cable, the link between 2 points. If you get rid of this single edge, boom, the network fragments. It was the one and only path connecting 2 parts of the system.
And this is where it all clicks into place. An articulation point is a critical node. Think of a huge, busy city intersection. A bridge, on the other hand, is a critical edge, like that single, lonely road leading to a remote town. They both have the same devastating impact, right? They fragment the network. But what they are, a point versus a path, is fundamentally different.
Okay, so we know what we're looking for, but how in the world do you actually find these things in a massive, tangled network? Well, it turns out we have a really clever algorithm that acts like an explorer, methodically mapping out the entire system to find those weak spots.
But before our explorer sets out on its journey, a really important warning. This entire technique, everything we're about to talk about, is designed specifically for undirected graphs. That's where connections go both ways, like a normal two-way street. If you're dealing with one-way, directed graphs, you're going to need a completely different set of tools. So our Explorer's strategy is something called a depth-first search, or DFS for short. And as it travels, it does two really important things. First, whenever it gets to a node for the very first time, it stamps it with a discovery time. You can just think of it like the Explorer is saying, okay, I was here at second 1, then here at second 2, and so on. Second, for each node, it calculates what's called a low-link value. This is basically the earliest discovery time it can get back to, even if it has to take a weird shortcut, a back edge, to a place it's already visited.
And this is where the magic happens. Those two little pieces of information, the discovery time and that low link value, are literally all our Explorer needs to identify every single weak point in the network. This is the real aha moment of the whole process.
The logic actually boils down to two simple rules. First, there's a special case for the starting node, the root of our search. If that root has more than one direct child, it's automatically an articulation point. Why? Because taking it out would separate those children into their own little disconnected worlds. For every other node, let's call it U, it's an articulation point if any of its children, say V, has no way of getting back to a node that came before U. In other words, that child V is completely dependent on its parent U to stay connected to the rest of the graph. And this, right here, is the secret sauce. This is the entire logic of the algorithm in its purest form. We're just comparing the earliest reachable node for the child, low for V, to the discovery time of the parent, disk U. Whether it's greater than or equal to, or just strictly greater than, tells us everything we need to know.
Let's really break this down. If the child's low link value is greater than or equal to the parent's discovery time, that means the child can't find a shortcut to anything that came before its parent. The parent, U, is its only way back up the chain, which makes U an articulation point. Now look at the condition for a bridge.
It's strictly greater than. This is even more isolated. It means the child V can't even get back to its own parent U through any other path. The edge between them is the one and only way, and that makes that connection a bridge.
Okay, so we've got the theory, we've got the algorithm. But why does any of this matter outside of a computer science class? Well, because this logic is absolutely fundamental to building resilient, fault-tolerant systems in the real world.
I mean, the applications for this are pretty much everywhere. We're talking about making sure the internet stays up by finding critical routers before they fail. We're analyzing power grids to prevent those massive cascading blackouts. It's even used in city planning to avoid creating terrible traffic bottlenecks. And in cybersecurity, to find the one weak server that, if hacked, could bring down an entire system.
And you know what the best part is? It's incredibly efficient. The time it takes to run this analysis scales linearly with the size of the network. That's what that O of V plus E means. V is for vertices, the points, and E is for edges, the connections. It basically just has to look at each point and each connection once. This makes it super practical for analyzing even huge real-world networks.
All right, so let's do a quick recap of the most important stuff. This whole technique is built on a depth-first search. It cleverly uses just two pieces of data, discovery times and low-link values, to find every single point of failure in an undirected network. And really, understanding this logic isn't just some academic exercise. It's a foundational concept for building the robust systems we all rely on every single day.
So, we've learned how to find the weak spots, how to diagnose the sickness in an existing system. And that leaves us with a final, and maybe even more profound question. Now that we can find the weaknesses, can we use that knowledge to design truly resilient networks from the ground up? Networks that have no single point of failure at all? Now that's something to think about.